Did you see it?
Yes.
Yes, okay, thank you. So the second module is about control of microbial hazards. There are 4 levels. The first one, the basic level, is translated in 4 languages, and it contains 4 units, legislation and HACCP definition, hygiene indicators and pathogen, and origin of microbial contamination. The second level, intermediate level, is only in English and contains 5 units. About deviation, how to control deviation, validation of process, use of control chart, and cold chain management. And the advanced level is only in English too, and there are 2 units, statistical process and construction of control charts. About the hygiene indicators, microorganism. So the first question that we want to ask is, all microorganisms are bad, yes or not? And for sure the answer is no. We can classify microorganisms in three categories. The first one is good microorganisms, which are flora of technical interest that contribute to organoleptic qualities of food, or protective or biopreservation flora. You can find also bad microorganisms, and in this category we found microorganisms involved in spoilage that degrade the product, and also we can find hygiene indicators. And the third category is pathogenic bacteria. So what are hygiene indicators? Hygiene practice are a set of measures taken to guarantee the safety for the consumer, because food are subject to deterioration and microbial contamination that can harm the consumer. In the European regulation, a text implement the hygiene package that distinguish 2 criteria. The first one are safety criteria that define an acceptability of a product or a batch of foodstuff applicable to products placed on the market. And the second criteria are process hygiene criteria that define the acceptability of the operation of a manufacturing process. So here you have a screen of products. It's milk and dairy products. It's found in the Appendix 1 in the EC regulation. For each food category on the left, you can find specified microorganism, and you have the limits of contamination in the products, with the analytical reference method and the stage where these criteria are to be applied. So the process hygiene criteria are defined as the acceptability of the production process. Such a criterion is not applicable to market products, and it sets an indicative contamination value if exceed the FBO required corrective measure. So what criteria should you use? Some criteria are defined in the EC regulation by food category, as we shown previously, but other hygiene criteria are defined by the professional organization, sector by sector. So these references are defined by professional for professional. There are no regulatory value. They use nevertheless enable operators in the same sector, food analysis laboratories, and official inspection services to have common references. So the qualities required to find an indicator microorganism. These microorganisms are to be present and detectable in food. They have a present or a concentration correlated with poor process hygiene. They should be easy to detect or enumerated and easy to distinguish for other microorganisms. They should be counted rapidly, and they have a slow growth or inhibited by other microorganisms. Some hygiene indicators, when they are present, can be pathogenic, such as Staphylococcus aureus, Bacillus cereus, or Clostridium perfringens. And other microorganisms can be responsible for food spoilage. Some lactic acid bacteria or other Pseudomonas, Procotyrics, or some yeast or molds. Here in this table, we have listed some example of microbial targeted. In the first column, you can find hygiene indicators such as mesophilic aerobic flora, total lactic flora, or anaerobic flora. For each hygiene indicators, we resent the process step they can contaminate the products. And after, we put some example of the food concerned. We did the other example for Enterobacteriaceae that can find in all products manipulated, or E. coli that are an indicator of fecal contamination. And it can be also a presence of other pathogenic enterobacteria such as Salmonella. And Procotrix thermosfacta, for example, is only present in meats and in the raw materials. Some other example, Pseudomonas is mainly present in meats. Bacillus are present when the heat treatment is not correct. For example, and yeast and mold are mainly representative of environment contamination. So that's it for my short presentation, but there is more information about pathogen and hygiene indicators on the platform. Thank you.
Thank you very much, Viviane.
I'm Ursula González. I am going to explain to you microbiological sampling plants. But for this, I need to put the topic into perspective by providing you some basic definitions that I'm sure you know of, but are related to sampling. Then I will explain a little bit about acceptance sampling theory and the statistical aspects of this. You will learn what is an operating characteristic curve and the properties. And then, since there are many types of sampling plants, I am just going to focus on two types of sampling plants and to relate them to microbiological testing. So for definitions, I'll start making the difference between a true value and a measured value. This is very, very important in statistics to know that the difference about the true value and the measured value. So the true value is a known or accepted value for quantifiable properties. So in many cases, we do not know the true value of something. So imagine just the growth rate of certain microorganisms in food. So the growth rate, we know there is a value, that we know there is a populational value for that, also known as true value. But it is greatly unknown. Even if we repeat the experiments, we can obtain the measured value. And as soon as we conduct experiments that are reliable, we can get close to the true value. Okay, so then the next is accuracy versus precision, and this is very close to the previous definition. So accuracy indicates how well a measurement coincides with the true value. This is when we talk about something is accurate. We have an accurate measurement. It's different from a precise measurement because precise indicates how well a set of measurements coincide between them. So to talk about precision, we need a few measurements. in order to know if some estimate is precise. But measurements can be accurate, and maybe they are not so precise, or they can be precise, but they are not accurate, or maybe they are not accurate or not precise. So the best way to explain is by this diagram of the target. So in the first example to the left, you will see that this measurement is precise, because there you have three measurements that are very close to each other. Therefore, this measurement can be considered precise, but it is not accurate because we are not close to the true value, which is the center. In the next, we have measurements that are accurate because we have obtained measurements that are close to the true value, but between them there is no precision. And in the last case, on the bottom, the measurements are neither precise nor accurate. Okay, so now with these terms that I'm going to use, we are going to move to statistical quality control. So statistical quality control is a subdiscipline of statistics. And there are two main areas that are studied in statistical quality control. The first is a statistical control process, or I think there is a mistake. It should be statistical process control. That is the right term. And these are techniques to control the quality during production. This is something that you are going to see next in the next presentation. So these are techniques that are supposed to be applied during the production process. And they are mainly for monitoring the quality and to assess deviance from processes. The next is the acceptance sampling plan. So these are really a set of theories that are used for the inspection of a finished product. So there, it is about inspecting a group of products or a lot of products. And this is not done as in a statistical process control. This is not done to monitor, this is not to verify the quality. Therefore, the acceptance sampling plan or the sampling plans are applied only when we know that the process is under control. So it cannot be in a process that is chaotic. They cannot be applied in processes that are still chaotic. So sampling serves to make an inference of the state of the process. So we can know if a process is in control or out of control by obtaining a small sample from an entire lot of production. So there is also a huge theory of samples. So if you want to know how to sample, they can be done randomly, can be done stratified. So there is also a theory about something that seems so simple, and also a theory about how much to sample from a lot. So which is dependent on the lot, because this will drive the assumptions of your conclusion. If we want to go more technical, for example, it will allow you to assume if your sample follows a binomial distribution or a hypergeometric distribution, for example. So the acceptance sampling is a sampling. It is a big body of theory related to how to assess and how to design a sampling plan. A sampling plan is a plan that specifies the lot size, the sample size. The sample size means the number of individual sample units to extract from a lot. This is the sample size. So normally the lot size is defined by or indicated by capital N. The sample size is is N. The number of maximum defective samples is the acceptance sample, which is C. But we can have also other criteria of acceptance or rejection. So we can have sample a sample limit, for example, M or capital N, that would be more into microbiological sampling plans. But they have to do with the criteria. So it's like a threshold where samples are taken from a lot, they are analyzed or observed, and then this is compared to a rule, and therefore the lot is finally, we can say, classified as in conformance or non-conformance. It is a form of inspection applied to lots before or after a process to judge the conformity with pre-established standards. So that means that this acceptance criteria has to be derived as a function of these pre-established standards. To understand better about the probability of detection, because it is a term that we are going to talk about later, let us suppose that you have a population or a lot of 10 units, which is what you have, and 50%, so you have 5 units that are defective. So this is a very bad process. Then you have to extract only 3 samples from these, 3 samples. So the probability of defective, what will be the probability of detection of defectives? So the probability of detection is going to be very high, because what are your chances of choosing, of getting there at least one red ball? So the probability is very high. Now let us suppose that you have 10% effective. Now this is the representation of a lot where only 10% is effective. So in the 10 units, you have 1 unit, their color as red, where that is out of conformance. Therefore, the probability of detection there, if you take 3 samples, it will be less probable that you find that you classify that lot as effective, because it's only 1 sample. Now, this is more into reality. This is more into the reality of microbiological contamination in lots. So now suppose you have here 100 samples, and only you have less than 1% effective. So, and you have a sample size of 3. So the percentage of finding a non-conformal unit, it will be very, very low. So your probability of detection is quite low, but this has to be understood in the sense that when we analyze a lot, we have to remember that we are not analyzing any unit of the lot. So we are analyzing a sample. Okay, so that means that when you analyze a sample, there is a probability of detecting or finding, the probability of finding that the lot is non-conformal. Therefore, you have to understand that there is a risk, and this risk is known, or the complement of this risk is known as the level of confidence. So at least from this lot, you see, I can establish a sampling plan where I feel I am 90% confident that the defectives are going to be found, or that the batch is going to be classified as defective. So I need to know the confidence I have as a producer. But as I said before, the sampling plan is used when you already have a stable process, so that you can prove that the quality and safety of the product is good, or to the standards. So you cannot have, or you cannot apply, a company cannot apply a sampling plan when the process is out of control. Okay, so now I'm going to explain the statistical aspects of the sampling plan. So in sampling plan, if you check any textbook, you will find the operating characteristic curve as the most important feature to evaluate the performance of a sampling plan, but also to design. And the operating characteristic curve, as you can see, is a plot of a cumulative probability of accepting the batch. Okay, the cumulative probability of accepting the batch, conditional to the quality level on the x-axis. So the quality level could be the prevalence. If we want to move these in terms of microbiological quality, could be the prevalence. Quality of the lot can be expressed as the prevalence of certain microorganism, or can be expressed as the mean concentration of certain microorganism in a lot. Okay, so the operating characteristic curve always have this shape like that. So for every sampling plan, there is only one operating characteristic curve, and this is good because this allows you to compare different curves. So for example, here you can see 3 different curves. So that means that these are linked to 3 different sampling plans. One of the properties of the curve is how steep they are. So the steeper the curve, the higher the capacity to discriminate between lots. So performs better. If this, for example, this line that is of light gray color has lower discriminant capacity than the black line, than the sampling plan linked to the black line, and I will explain later why. So there are 2 parts or 2 points in a sampling plan that are very important to define. So to define as a producer or as a client. The first is the acceptable quality level. The acceptable quality level is linked to the probability of acceptance. Okay, so this means the acceptable quality level is a quality of good lots that should be accepted most of the time after a sampling plan. So the AQL is a level of quality that is good. Okay, so but it's in the limit. It is good, but in the limit of good. So meaning that the lots must have at least this quality level, at least. So it should be better. The producer should produce lots that are of better quality than the acceptable quality level. Okay, this is why it's called acceptable. And this lot should be accepted most of the time. So if we are going to design a sampling plan, this quality should be accepted at least 90% of the time, for example, because I'm seeing this alpha, which is a risk. So the risk will be 1 minus PA, 1 minus the probability of acceptance, or 100 minus. So this means that the alpha, which is risk type 1, or error type 1, is 1 minus the probability of acceptance. The interpretation is the risk of rejecting a good lot. Okay, there is always a risk because you know that the lots, that the units of a lot are not analyzed entirely. So you take a sample. So there is always a risk of there are risks of misclassification, but this is the risk that is not too bad. This is type 1 risk. Then you move on to the next point, which is LQL. LQL refers to the limiting quality level. What does that mean? That this is a very bad batch. So, but it's in the limit also. So in the limit of rejection. So this quality should be rejected most of the times, meaning that the client or the consumer has a 1 minus beta % confidence that this lot is going to be caught by the sampling plan. The sampling plan should be able to caught this lot. Okay, so, but now it is 1 minus beta. For example, if we set beta, the consumer risk to 5%, we are saying that this quality level, this limiting quality level, must be spotted with a confidence of 95%. So how do you understand the term confidence in statistics? Means if you repeat the experiment 100 times, 95 times, this lot has to be spotted. And there is a risk that 5% they will go through, they will not be detected. So, but it is assumed that the producer is operating at a fallout level that is considerably better than the LQL, even that the producer is operating at a quality that is much better than the AQL. Okay, so it's operating in this area to the far left-hand side. And that is so here in this slide, I'm just summarizing the error type 1 and the error type 2. The error type 1 is normally set between 5 to 10%. And the consumer's risk also. But maybe it's safer to set this risk to 5% because this is the error type 2, which is worse because it means that this very bad quality lot can be accepted at the 5% probability. So it's better to set 5% probability of acceptance than 10% probability. So what was I saying earlier here? Than the steeper, the better. So this, I'm saying that this black line is a steeper. You see, it's steeper than this light gray line, and therefore it has a better discriminant capacity. It is very easy to understand that if you suppose that in a lot all the units are analyzed. Suppose that in the lot all the units are analyzed, and that you set the acceptable quality level to 2%. If you analyze all lots, then you will know that lots with quality lower than AQL will be accepted because you are analyzing all. There is no errors. And all lots with a quality worse than AQL are going to be rejected. Therefore, when you make your plot, you will have a straight line. Okay, so this is fully discriminant. What are the sampling plans used in microbiological testing? So the definition is similar. The microbiological sampling plans are based on the acceptance sampling plan theory. Also, the lot refers to a batch of products, and these products are manufactured under the same conditions. And also, there is an assumption that during sampling, the samples should be taken from the lot independently, so they are not dependent one from the other, and also randomly. A microbiological criterion is a set of parameters used to define the microbiological quality of raw materials, food ingredients, and products at any stage in the food chain, and they are laid down in the regulation 1441 of the European Commission. The establishment of a microbiological criterion is useful for verifying. So here you have, this is the important word, verifying that food control systems are implemented correctly. So acceptance sampling plan can never be understood as a tool for classification. It's not a classification, so it's a verification. So that means that they should be always passed. And within the paradigm of food microbiological safety, the microbiological criteria are like a bridge between the food safety objective or the performance objectives and what is happening at processing level. So in terms of classification, there are two types of sampling plans. Sampling plans by attributes and the sampling plan by variables. In microbiological criterion, we are using the sampling plan by attributes. Okay. The big difference, between these two big groups is that the sampling plan by attributes are based on statistically they are based on binary data. Okay, they rely in the binomial distribution. There are inside the sampling plan by attributes. There are two types of sampling plans: the 2 class and the 3 class. You will know the 2 class because you will have at most 3 parameters. So you have the sampling plans based on microbial prevalence, where you will have as parameters the sample size and the acceptance number. The ones based on the microbial concentration, where you will have additional the microbiological limit M, and those based microbial prevalence with an enrichment step. So this makes difference in the statistical calculations for assessing the performance of the sampling plan. And there because you are talking about enrichment, you will have a sample weight. And then you will have so that means the 2 class is a big group. The 3 class consists on those sampling plans that have a lower limit and an upper limit. So you will have two M's, okay, 2 limits, a lower and higher. And then comes the sampling plan by variables. The sampling plan by variables within what is microbiological criterion, they have been widely disregarded. So they are really not used a lot. They should be, because the sampling plan by variables provide much more information actually than by attributes. But I will explain two types of sampling plans. So I will start from the simplest, which is the two class attributes, this one based on the microbiological prevalence, so N and C. You have there two parameters. You have N, the sample size, and C is the acceptance number, is the maximum number of positive samples, which in terms of pathogenic bacteria is set generally to 0. This is a stringent sampling plan to assess the presence of pathogens. And when a lot fails to comply, then the batch should be rejected, meaning reprocessed. Okay, so this is you can see the operating characteristic curves for this kind of sampling plans, and I would like you to have a look at the N. So C is constant to 0, so that means that no positive, the rule is having no positive, and then you see that N value is decreasing. So when N is fine, you can see that the sampling plan is not as discriminant. No? It becomes slowly, as you increase the sample, it becomes more discriminant. Now C is normally set to 0 for pathogens. Now let us think of this sampling plan. N equals 30 samples, C acceptance number 0 for a chronobacter in powder infant formula, which has really, if you look at the regulation, you will see that it is 30 and C is 0. So if you look at this operating characteristic curve, you'll check you can find what is the LQL for a factory. So the limiting quality level for a beta risk of 5%. So if you set a beta risk of 5%, you have to check up in the table. The probability of acceptance is 0.05. So you can determine this is the limiting quality batch or true prevalence of 0.095, 9.5%. This means that such sampling plan would give a confidence, you see the word confidence, of at least 95% of rejecting batches that have 9.5% or more defective units. In this case, would be the chronobacter. So in statistical terms, this is based on the binomial distribution. So you do not need actually to determine the sample size or the probability of acceptance a batch. You do not need to make this graph because calculations are simple because they come from the binomial distribution. So the probability of accepting a lot will be the probability of having no positives, C equals 0. And this is the probability. This will be the binomial probability where D is the true prevalence and N is the sample size. But you see from this expression, that means that we can determine the sample size if we work out the equation N equals. So we will need to know the probability of accepting the lot, which can be set by the producer. And of course, the producer will have to have an idea of the lot that at maximum, what is the percentage of prevalence. This is a value that the producer has to know from historical data. But then you will see this equation. This is a very interesting equation. It is possible to estimate the confidence limits for the true prevalence of contamination at a given confidence level, which is 1 minus alpha, when all the sample units test negative, okay? This is the requisite. So that means that your confidence limits are bounded between 0 and DU. And with this equation, you can determine the upper limit for the true prevalence, okay? And if you have this value, you can also determine, you will have the weight, which is the amount of sample analyzed, and knowing the upper limit of the true prevalence, you can also determine the mean concentration of the lot, which will be the limit of this, what is about the lot. So here I have an example for you how these equations can be used. Suppose that you wish to derive a sampling plan to test salmonella in frozen chicken. And suppose that the performance objective is formulated as not more than 50% chicken carcasses in a batch may test positive for salmonella. So that means this is your value. This will be your value of D. Okay, and then they give you the confidence. The confidence that a defective batch is rejected should be set to 95% probability. This means that the probability of acceptance is a complement, because you want to reject 95% of the time. So your error is your beta error is 5%. Your probability of acceptance is 5%, 0.05. Okay, so this is the data you have from the problem, and you replace in the equation, and then you can determine the sample size. It means that you should take at least 18 from a batch. You should analyze 18 carcasses at least, or neck skins. Now the other question is to use the other equations. What is the maximum within lot mean salmonella concentration in frozen chicken that ensures that 95% of the time a batch is level of compliant? What is its maximum that ensures that you are not rejecting the lot? Do you understand this question? So as a producer, I want to know what is my limit, so that most of the time my batch is accepted, and I know that I use 5 grams in the analytical determination for salmonella. So this is just a matter of replacing in equations. You have to find the upper limit for the prevalence. You have alpha, which is the risk. So the upper limit will be 15.3%. Knowing the upper limit, you can use the fourth equation, and you know that the weight is 5 grams. Therefore, you can determine the limiting quality level of the batch, which is 0.38 CFU per gram. You may think this is very low, but this is frozen. This is frozen chicken. And then lastly, I will give some explanation about the 2 class attributes based on concentration. And there you will have one more parameter, which is the microbiological limit, but is commonly expressed in absence in certain sample weight. Okay, but you may wonder how is this done, and I'll explain later. I have said that the 2 class attributes are based on the binomial distribution. Yes, but and here you can ask me, but why you have a microbiological limit? So like a CFU per gram, it's not it's not binary data, it's concentration data. What happens is that the 2 class attributes it categorizes the data into acceptable and defective. Okay, so here again, you will see 3 operating characteristic curves for a 2 class sampling plan, where n increases, and you see the rule is the same. So if you look at n equals 15, your sampling plan is more discriminatory, has a better power of discrimination, because the curve is steeper. Now, there are some assumptions when you use this. So when the result of a microbiological analysis is given in a quantitative manner, for example, CFU per gram, or most probable number per gram, you have to assume that the concentration of the microorganism, the low concentration, follows a normal distribution. But this leaves us with an additional assumption, because the normal distribution is defined by mean and standard deviation. Now the assumption is, what is the standard deviation of these of the microorganisms in a lot? Okay, you have to have data to determine that, or you can assume according to how homogeneous are the microorganisms spread in the lot. So normally when the food is liquid, for example milk, you can assume a sigma 0.2. If the food is of intermediate homogeneity, you can use 0.4. Imagine now you're working with carcasses, meat carcasses, then you can assume that your standard deviation is between 0.8 to 1. So if you go for 1, you are assuming that your bacteria is highly clustered. Then the limit M. The limit M is the detection limit of the analytical procedure. It could be, if you are using a plate counting technique for Listeria, for example, you can use an M equal 1 if the limit of quantification is 10 CFU per gram. Now imagine you are using a 3-tube, most probable number testing protocol. Therefore, for 0, when you get 0 in the 3 tubes, the limit of detection is 0.3 CFU per gram, and if you take the logarithm of this amount, it's minus 0.52. So in this drawing, what you have is a normal distribution, and I want you to observe that M is divided the lot into a proportion of acceptable food units and a proportion of the effective food units, which means that what you're doing is to discretize. You're discretizing your results, you're losing information, but it is actually what is done in the microbiological sampling plans, because the variable sampling plans are not used. And before I forget, I would like you to put some equations if you ever would like to design an operating characteristic curve for this sampling plan, so you can do it easily. If you fix in Excel the cells N, Z, the acceptable number N, microbiological limit, and sigma. And then you'll have to provide in the spreadsheet values for mu, which is the mean concentration of the lot. So these mu are values alongside the x-axis. For the probability of acceptance, then you can use this formula in Excel. Here, you need the probability of acceptable units from the lot. But you use 1 here because it's a cumulative probability. For the proportion of the effective, it is the complement. So it is 1 minus PA, so 1 minus this value. And then finally, you can calculate the probability of accepting the lot, which allows you to know the probability or the degree of confidence that your good lot is accepted, or the degree of confidence that your bad lot, the very bad lot, is rejected, and you use this function using the binomial distribution. Okay, so I think this is all from my side, and I hope I was clear showing to you all these maths. Thank you.
For this comprehensive presentation of sampling plans. The next speaker is Vasco from the same institute in Portugal, who will give a presentation about control charts. Vasco, the floor is yours.
Thank you. Good afternoon. So my name is Vasco. I'm coming from the Polytechnic Institute of Bragança, and I will show you how to use the control charts to control the processes in food industry. I would like to know what to is okay. Good. So this is the content of the talk. We'll start about the statistical process control, talk a little bit about this set of statistical tools to control the processes, and also talk about a little bit about the statistical aspects of control charts. We'll talk about type of variables that we can use on the control charts, and then we finish with some conclusions. Okay, the statistical process control. All the processes, we can find some variation in the products, and this variation can have two main causes. They can be random, and if they are random, we cannot do much about this because we cannot control them. They are random, and there are other causes of variation that we can assign or attribute to some specific causes. In this case, we can intervene and we can control these sources of variation. So these random causes of variation, they are present in all the production processes, and they are thinking as a natural variation. So there will be some unexplained variation around the target value. So, for example, the final moisture content. So we have some tolerance about this design of the product, and we allow for this natural variation or random variation. So the process will be in control when the products that we deliver have this, are within this natural variation. We call this tolerance. So the process is completely stable and predictable if the results are within these tolerance values. Sometimes these assignable causes of variation, they can have impact on the products, and we have variation higher than these random causes. So this variation is not inherent to the process, and they are indicating that something is unusual is happening in the process. So, for example, we can have problems in the raw materials that are arriving to the factory. We can have non-trained food handlers or even faulty equipment. So when this happens, the process goes out of control, and we need to take some action to bring the process in control again. So the process, if is affected by these causes, can be unstable and unpredictable. Okay, so how do we see that the process is in control? This brings us to the normal distribution and to the theorem of central limit. If you have a big data set or a big sample, then we can assume that the data will follow a normal distribution. If you take a look to this figure, you can see that normal distribution has nice properties. If you plot the mean and the interval of -3 standard deviation and the mean plus 3 standard deviation, we know that 99.7.8% of the data should be in this range. If you go to the 2 standard deviation, we know that 95% of the data should be in this range. And for 1 standard deviation, 68%. So we know more or less the variation that we can have. Of course, if the data, if one point goes up to the right side, higher than the mean plus 3 standard deviation, we can imagine that this point can be suspicious. The same for the left side. So we can use these properties of the normal distribution to check if the process is in control. So most of the process we have a target value. Usually it can be the mean. It can be other statistical measure. And the variability present in the process in control is inherent to variability, that random variability. So we can use can measure this variability using what we call the standard deviation. As you know, the standard deviation is the measure of variation within a random variable. So for the purpose of statistical process control, we want to give some signal of the process mean. If the mean moves away from the target, then we can check our process and check if the variability is stable or if this variability is increasing. So in either case, appropriate action we need to take in order to check or to control the process. In this figure, you can see a process that is in control. If you take a look, we can see that the variation due to common causes that we call random variation. In this case, all the distributions along time, they have the same location. Let's say the same mean in the same size or the same variation. If you take a look to these three distributions, they have the same range, the same variation, and a similar shape, the same shape over time. So this process is in control. Contrarily, this picture shows you a process that is out of control. You look at the picture, we have different means, we have different variations, what we call and different mean is location, the size of the variation, and the shape is also changing over time. So this process is out of control, and we need to take actions in order to bring this process to in control. Another example, in this case, if you take a look to the solid line and the dashed line, they are parallel, they look nice, but if you look to this process, you can see that there is no variation in mean. The mean is stable along time. There is no variation in spread. The variation of the distribution is similar. The process is stable, in fact, but the process is off target. Our target is the solid line, and all our samples are on the dashed line. So this process is off target. Of course, if we need, looking at this picture, we need to take some corrective actions in order to bring the process in control. Another example, in this case, the solid line and dashed line, they are moving along time, they are connecting along time. So you can take a look at this. There is no variation in the mean. The mean is the same. There is no variation in the spread. The variation is the same. The process is not stable because the mean is evolving along time. No? There is a shift on the distribution along time. So this process, you can look at this as a process being improved. So maybe we are starting our process, and during the first batches, we are adapting the process, and we are, after some time, getting the target, and after that, we can check the process and the quality of the process. So usually we use what we call 7-step process to use in this statistical process control, and these 7 steps can be enumerated as you see in this figure. So we start with the investigation and benchmarking the process, or the current process that we have, check the process. Then we need to identify the variables that we can measure that are relevant for the process. After this identification, we need to check if we have available resources to do the work or to improve the process, or to check the process that we have in place. We have the resources that we can apply the methods and then collect the data and apply the appropriate statistical techniques in order to check our process. So we have the data, we have the statistical tools, we can monitor and identify the variables that we define in the step 2. So if you have in the step 6, if you have problems, if you identify problems, we need to implement corrective actions. If not, we can go to the 7th step, and if you have an outcome that is successful, then we can standardize the changes and we can define the final product. And of course, if we need to repeat this process, if we want to improve our product, we need to go through this process again. So there is a relationship between food safety control and the statistical process control. And usually the food companies need to verify the food production. So they need to check if the products are presenting, they have the expected characteristics. So this is important also to demonstrate that the process is in control. Of course, this process, we call this process control verification. So this is a verification test that the companies can do, or they do and should do. And this verification testing can be done in different steps of the production system. No? Can be in the reception of raw materials, can be after stuffing, can be after fermentation, if we think in a sausage production, for example. And of course, we need to define this in order to check the most important points to do this verification test. Of course, in the end product, there are also some regulatory verification. So the authorities can check the product to see if the product fulfills some microbiological criteria, and can be used also by the industries to check if the upstream process is under control. So we can predict the end product based on some characteristics of some controlling, for example, of pH after fermentation or water activity after smoking, for example. Okay, so the next step, why we should use, or food companies should use statistical process control. First, to monitor the manufacturing processes. So this statistical process control will give operating personnel a tool to identify when a special case of variation is occurring. So if we have this signal causes of variation, then we can check the system again. For example, more contaminated raw materials can impact the final product, the contamination of final product. So we need to eliminate this cause by testing the raw materials. Of course, we can use this process also to eliminate the constant tweaking of the process. So it is helpful in identifying opportunities for improvement that can lead to reduced variation. Usually, we want reduced variation or less variation. Maybe in some process we want to have more variation if you want to have different targets. But usually we want to reduce variation in our products. So the process that are gathered aimed at the quality safety target. So we want to improve the safety. Okay, we want to also to comply with the requirements. There are some requirements that we need to comply with, so we can use this statistical process control to satisfy the client requirements, to meet certification requirements, or to target the safety or process in order to meet microbiological criteria. And finally, we can use these tools to conduct a continuous process improvement. We check and we can improve our process. So if the control is achieved, the aim should be to reduce variability. We can check and try to reduce variability as much as we can to make the food products more consistent and microbial concentrations more predictable. This is very important also. So now I will show you some control charts that widely used in the food industries. And we need to collect data during the process. And after data is gathered, then we can detect variations. Then we can intervene in order to control these variations. So the control charts are in fact dot plots or dot charts where you plot, for example, the mean. As you can see in this chart, the dot is the mean, and we define the upper limit and the lower limit. And in the line, we have the optimal point or the central limit or the control limit. So we use these control charts to evaluate or to identify the type of variation in our process. So we can use these charts to check if our process is in control. How do we implement control charts? We start with the process in control. So we need to have the process well defined and in control. Then we define the control points where we need to collect data. This is very important. After we define the most important points where to collect data, we start to gather the data. Let's say 15, 30 lots. We usually use it to define the baseline for our control chart. And then with data, we construct the control charts and use these control charts. They are updating a long time and use this to monitor the system. Of course, if something is wrong, then we need to adjust the process or even the charts, depending on the information that we have available, as you will see in the next slide. So when we study statistics, we learn about the type of variables, and there is continuous variables, there is categorical variables. In this case, we call, when we talk about continuous variable, in this statistical process control, they define these as variables data. If you are talking about the categorical data, they call these attributes data. So in the variables data, we have continuous scale. So we can assume normal distribution if you have a big sample. And as example, you can have the net weight of final product, pH. You can use it also for control the temperature in the cold room or in the mesophile counts, for example. So in this case, the name of this type of charts or control charts is control charts by variables. If you are using discrete or binary or categorical data, then these data follow a normal distribution. Example, contaminated or non-contaminated swabs from an equipment, number of defective units. So in this case, we call these control charts by attributes. There are a lot of different control charts that you can construct, but for our case in the food industry, there are 4 or 3 main charts that you can use. That depends on the type of variables, as I said before, and depends also on the sample size. Usually we don't have big sample size, so we use X bar and R bar. X bar is the mean and the R is the range. If the sample size is small, instead of computing a mean, we use the range in that sample size, in that sample. Of course, if we have a big sample size, then we can go to the mean and the standard deviation, but usually we don't have samples higher than 10, so we rely on this X bar and the R bar. And if you are in categorical variables, usually we use these proportions, defective, and there is what we call P chart and then P chart. The difference between these two is connected with the sample size. If the sample size is always the same, you can use a P chart, but if the sample size is changing over time, then we need to do NP chart because the sample size has an effect on the calculations. Okay, so the type of charts are summarized in this table for the attribute data. So you can see the P chart and the P chart binomial. I already explained this. For the variable data, you can use the X bar, R chart, and also some individual chart, but is not very common. In this case, the I chart is when you have just one, you analyze just one unit, then you use this individual chart, but it's not very common to use this. So now let's explain the X bar chart. So this is a plot with means of the sample. So you can see in this example how it will look like the implementation. So the X bar chart, we need to, of course, compute the mean, and the mean is we collect a sample from the lot, and then we compute the mean, arithmetic mean. So this is not very complicated. So we have the mean of the sample and we plot the mean of the sample. And the evolution along time will show you if the process is in control or not. Of course, we need to compute what we call sorry, the limits of variation, and these limits of variation can be 2 types. What we call the lower control limit and the upper control limit. In this case, we use the, if you remember the normal distribution, we use the variation between the mean and plus 3 standard deviations, or mean minus 3 standard deviation. In fact, we use the standard error. If you take a look to this lower limit and upper limit, we have the mean minus 3.0. This 0.0 is the number that we need to multiply the standard error in order to have this variation in the normal distribution. And sigma divided by the square root of n is the standard error. So you can use this or the standard error itself. Of course, this is for the 3 sigma, but we can use also the 2 sigma as a warning limit. Let's say if we put today you can have a system that collects data and the system can give you some warnings if the value is above this 2 sigma. For that, you can use these warning limits that you can see here. The upper control limit, the lower control limit, and we have these two warnings at 95% or to sigma. The P chart is similar, but of course the data is different. In this case, we are computing a proportion. So we collect 5 samples, and we see how many of these 5 units, and we see how many of these units are positive or negative. So we compute this proportion. The proportion is the positives divided by the sample size. So the sample size N. Okay, you can put the proportion. In this case, you can see that this dashed line is varying a long time. This can happen if your sample size is varying a long time. So if you collect a sample of 5, then a sample of 7, then a sample of 4, these limits will vary with the sample size. So if we have always the same sample size, this line will be a continuous line. So to construct this P chart, the process is the same, but we need to use the correct formulas because this P chart is based on the binomial. You need to compute the mean. To compute the mean, the proportion, the mean proportion, just sum all the positives, divide by n, you have the mean, and you need to find the standard deviation. In this case, for the binomial distribution is this formula, and of course then you need to compute the lower limit and the upper limit. In this case, you can use the mean minus 3 sigma and the mean plus 3 sigma as control limits and warning limits to sigma, so for the 95% interval. Okay, let's explain this. So how can we recognize if a process is in control? Okay, we can have several ideas to check this. First, at least one observation is outside the control limits. So if you take a look, this observation is out of the control limits. At least 2 successive observations are out within the same warning limits. So if they go out 2 observations out of the warning limits, we need to take care. 8 or more points in a row, either on either side, let's say on the top or on the bottom, are of the central limit. So we need to check all these tendencies. 8 or more points in a row trending in the same direction. So if the process is always in the same direction, something is wrong. What we expect a random variation along this central limit. So if the process, the mean is varying around this central limit, is good. If you take a look at this, our process is not in control because we have a lot of samples on the upper side. The similar here, you see a lot of means or a lot of values on the lower sides of the control limit. So this is, we need to take some action. Of course, if we see some cycles or recurring trends, something is wrong. So we expect a random distribution of these dots around the central limit. Okay, to conclude, control charts can only be implemented when the process is in control, so you need to have an in control process. In addition to control limits, a control chart can be also used to build warning limits. Today you can use it with the informatics system. You can have automatic warnings. A process being in statistical control does not necessarily indicate that the process is good or safe enough for manufacturing. A further condition is that the upper limit or the lower limit of the X-bar chart must be inside specification limits. So we need to guarantee these specification limits. For variables data, this is continuous variables. The type of charts that can be viewed for monitoring food processes are the X-bar, the R-bar, R-chart, R and I charts. For attributes, that is categorical variables, the type of charts that can be viewed for monitoring food processes are the P and the NP charts according to the sample size.
Thank you very much, Vasco, for all these details about the control charts. We are supposed now to have the question and answers session, part 2, but I'm afraid we don't have any question. We have not received anything from the online audience, but we have a surprise from our colleagues. We have some let's say, this kind of questions that you usually receive regarding this kind of topic. This is about auto controls. Would you like, Catherine or Valérie, to have this question? Should you read it?
Okay, so in auto controls, if the total flora exceeds the microbiological criteria, should I withdraw the production batch? So, response 1, now corrective action are to be implemented. And response 2, now if there are biopreservation flora or fermented products with a high count per gram, then the total flora shouldn't be integrated in the microbiological criteria.